Alright, let's see if we can finish up this lecture and get the last thing done today. So where we stopped in class, we were talking about how we charge a capacitor and the expression that we have for the charge and how it changes as a function of time. Notice that if we had the circuit with the battery, the resistor, and the capacitor. When the capacitor is fully charged, the potential difference across the capacitor will equal that of the battery, and then using the expression that for capacitance, the definition, the charge would be equal to C times V, which is the EMF of the battery. And so you see this expression right here. This is the total charge. So this value right here is C times the EMF. And this expression right here is you're taking 1 and you're subtracting from it a number that gets smaller and smaller as time goes on. And so that this value in parentheses gets closer and closer to 1. And so we're sort of doing this asymptotic approach to the total value for the charge, and that's what the charge looks like as a function of time. When we took for the current to find the time derivative of the charge to find the current, we found that the current, remember, starts off at the maximum value with all the current going through the resistor. So I naught, the initial current, is the EMF of the battery divided by the resistance. But as the capacitor gets more fully charged, the current goes down and exponentially decays. In both of these expressions, the product of resistance times capacitance is called the time constant. Those units multiplied together actually have to have units of time, so they would be actually units of second, because this whole exponent can't have any units. And that just tells us, gives us an idea of characteristically how quickly our capacitor gets charged and how quickly the current falls off. So there were some questions related to these things. One of the questions in the pre-lecture was if you have a resistor and capacitor connected in series with a battery, when the system reaches steady state, that means when time is basically like infinity or a very, very long time, what is the voltage across the resistor and the capacitor? So take a moment, pause, and see if you can think about what that would look like. So remember that when the capacitor becomes fully charged, the potential difference is equal to the potential difference of the battery, or the terminal voltage of the battery, which means actually that there is actually no potential difference across the resistor. It's all across the capacitor. And so that leads us to conclude that the answer is that the voltage across the resistor is 0, and the voltage across the capacitor is equal to the terminal voltage of the battery. In this question, we have a battery, capacitor, and resistor connected in series. Which of the following affects the maximum charge stored on the capacitor? So take a minute and think about that. Okay, so remember, when the capacitor is fully charged, the potential difference across the capacitor is equal to the EMF of the battery. Our relationship that we find for charge, capacitance, and voltage looks like this. So the charge of the fully charged capacitor is related to the capacitance and the EMF of the battery. And so our answer for this problem would be both A and B, the EMF and the capacitance. All right, we're going to actually just skip. Question, the next slide. And so here we have, we're going to talk about discharging a capacitor. So the idea here is that we start with a capacitor that's fully charged. And what we're going to do is, in a sense, the capacitor actually provides the charge that will become the current flowing through the circuit. We don't actually need a battery. So we take the battery out of the circuit, and so when we just have a resistor and a capacitor connected in series with each other, that's how we would discharge the capacitor. So we can think of sort of extremes that would happen in this case. So at t equals 0, the charge on the capacitor is its initial charge. The current in the resistor is 0, and the voltage across the resistor would also be 0. And what's going to happen at the end, at t being a very long time, is the charge on the capacitor is going to go to 0. Interestingly enough, the resistance, or the current across the resistor, will also be 0, as will the potential difference. So it's a little bit different than when we charged the capacitor. So what we're going to do is we're going to think about closing the switch, so that as soon as we close the switch, that will actually give the electrons a way to sort of leave the plates of the capacitor that they've been stored on and start moving around, creating a current. And so we're going to do a similar expression or approach as we did last time. Think about the loop and the potential drops and gains. Of course, as we go around the loop, we have the current through the resistor times the resistance is the potential across that, across the resistor, and then the potential across the capacitor is going to be Q over C, and those add up to be 0. The current, of course, is dq dt times R plus Q over C equals 0. And so now we want to, again, rearrange this so all the Q's are on one side and all the T's are on the other. We'll start with fully charged and go to some arbitrary charge Q, and that's the limits as t goes to 0 to some arbitrary time t. So let's go where we have more room. So what we were looking at was Q. So this is the natural log of Q, evaluated at Q and Q naught, is minus T over RC. This is the natural log of Q over Q Definition, natural log, it's e raised to the minus t over rc. It's equal to q over q, big Q. So q as a function of time is equal to the original charge, e to the minus t over rc. So this time we see what's happening is that the charge is exponentially decaying, similarly to how the current decayed in the last case. So we can take what it looks like. So it starts off at the maximum charge, it's going to drop off. Again, R times C is our time constant. If I want to look at the current is equal to the derivative of Q with respect to T. So what I'm taking the derivative of this time, okay, e to the minus t over rc. So this is what the current looks like with respect to time. The negative sign is simply because the direction of the current is opposite to the direction that we assumed. But if we go back to the expression that we used to find, that we did to integrate to find the expression for charge, which was I times R plus Q over C equals 0, we could talk about, okay, well, when T was 0, when we first started, the charge was actually the full charge, and so this would be I times R plus Q over C equals 0. We could rearrange this and find the current for T equals 0 would be equal to Q over RC. And look, that looks familiar right there. That's just the initial current. So we go and we just look at this expression. So again, for the current, interestingly enough, in both charging and discharging a capacitor, is something that starts at a maximum current and then exponentially decays with the time constant. Okay, so I just thought we'd look at a little example here. So we have a circuit with an EMF of 245 volts, a resistor of 75 kiloohms, and a capacitance of 4.6 microfarads. So this idea is, okay, so what does the circuit look like immediately after we complete the circuit? What is the voltage across the capacitor, the resistor, the charge on the capacitor, and the current through the resistor? So remember, we want to remember what happens when we first start charging the capacitor. At t equals 0, the voltage across the capacitor is 0, while the voltage across the resistor is equal to that of the EMF, which would be 245 volts. The charge on the capacitor, of course, when we first start is 0 because we haven't charged it yet. And the current through the resistor is simply, using Ohm's law, is the EMF over the resistance, which would be 245 over 75 times 10 to the third. And I think I have a number for that. The current is 32.7 milliamps. Now the other question is, what would be the situation for a long time after the circuit is complete? So this is when the capacitor is fully charged. So when it's fully charged, remember that at that point there's no current flowing, so the potential across the resistor is 0. The current across the resistor is 0. The potential across the capacitor is that of the EMF, because it's fully charged and it's 245 volts. And the charge on the capacitor is equal to C times E, which would be 4.6 microfarads times 245. And so that charge ends up to be 1.13 millicoulombs. All right? And that is it.